Hello, what? July 25th. Alright, let's do this. Find the city with the smallest number of neighbors at a threshold distance. There are n cities, 0 to n-1. And we have edges from, to, and weight. Represents a bidirectional, so there's no direction. Weighted edge between cities from and to, and given the integer in distance threshold. Return a city with the smallest number of cities that are reachable through some path and whose distance is at most distance threshold. If there are multiple such cities, return the city with the greatest number. Notice that. So as long as the small or equal to this, it'll be fine. Notice that the distance of a path connecting cities I and j is equal to the sum of the edges weights along the path. So in this case, distance threshold is 4. So what we want to find is the city with the smallest number of cities that are reachable through some path whose distance. So like for 1, this is 3, this is 3, this is 2. So for 1, we have 3. For 0, we have only 1. For 3, we have 2. For 2, we have... So the answer shall be... output is 3. Oh, 0 can go to 1. Or it can go to 2. I see. Got it. So 0 is 1, 2. 1 is can go to like all of them. 2 can go to 1, 3, and then, yeah, they can go to all of them. 3 can only go to 2. Just 1, right? 1 and this. And 0, 3 have 2 neighbor cities at a distance of 4. But we have to return city 3 since it has the greatest number. Holy crap. So basically what we need to do is to find all right. Well, I'm glad you find it interesting. Well, sometimes I struggle and it's actually not that interesting for me. All right, so what we need to do is to find the nodes which has the distance, right, smaller or equal to this. Well, because the n is only 100, maybe we can go through... Can we go through everything? I mean, I guess you can, because it's only 100. So if I set, 0 as a root, and we start to... BFS, DFS, doesn't matter, whichever way you want to go. You want to go through everything, visit everything. Now the thing is, it's based on this threshold, which means when you do DFS, alright, when you do DFS, as long as you don't go back to the one you already visited, which is fine, so you just DFS, and once it, like if I go from 0, I go to 1, which current, so I have to get the path that has been visited and also the sum of the weight. And once the weight goes beyond, then we just end. So we go to 1 was fine, and from 1 to 3, that's bad. Right, so we just cancel it. And we'll go back to 1, and we go 1 to 2. So now we kind of count, okay, we have 2 neighbors. And we can do that from every single one. Because n is only 100, right? N is 100, so we can do from each one, we go through everything, so that's O(n) squared. So I can do this with O(n) squared and store the number of cities for each one. And n is this, right? So I can have a counter for that. Okay. Let's try. I think this will work. Simply because n is very small. I wonder if there's a better way for doing this, but for this one, this is what I'm gonna do. Because n is small, so I just go for it. So I need a graph first. Can I use graph like this? Probably not. What I want is sum to sum. Yeah, I don't think so. We probably have to use a map. I don't think we need to go. I don't think we need to go there. Dijkstra. I mean, yeah, I can see Dijkstra, but I don't think we need to go there. Let's see. Let's get a graph. Let's get a graph up. So E of edges. So edges is going to be. What's the edges? Edges is from, to, and await. Okay, from, to, and await. So what I'm gonna do is graph.put 0, right? And oh, actually no. Okay, I'll put if put. Let me redo this. Graph dot. Huh? I cannot wait. Graph dot. Oh, my bad. There's a typo here. Put if absent, right? E0. Yeah, E0 and new list, array list, right? And graph dot put. Hold on. Put if absent E1, because we have this no direction array list. Okay, and a graph dot get E0 dot add new int. So I'm gonna do E1 and E2, and graph dot get E1 dot add new int E0 and E2. Okay, so this is we get a graph. Next we need a DFS. Okay, private. Let's go void DFS. I need graph, right? I need a node. I need a set of scene, and I need int weights, right? And I need something more. Okay, I need something more. I need, what do I need? The number of cities. Oh shoot, I need the distance threshold as well. And I need city counter. How about that? Okay. So we're at a current node. Oh, hold on. That doesn't feel right, because your DFS. Oh, I need to put the root. I need to know the root. Shoot. Okay, so I need to know the root. There's a current node, and I need a root. My goodness, you just keep putting everything in there. Whew. So at a current node, because when I get to the current node, that means current node can be reached. That is, yeah. If I can reach the node, that means if I get to the current node, it means it can be reached, which means the first call will be city counter, root will be plus, right? Because I reach the current node, and then from the current node, I will go to its children. But where do you update the scene, and then where do you update weights? I will update the scene and I will update the weights as I'm going through to the next one. Yeah, this is how I like to do it, which means I'm gonna say for int child cw child weight of graph.get or default node, right? And here is going to be, what is here? Here is going to be just I can do collections dot empty list. Okay, so I do this. All right, good night. Thank you for joining. All right, so we're getting the CW, which is a child and a weight, right? And I need to say if, don't worry about it. It's okay. If scene dot contains CW0, if it does not contain, right? If it does not contain, all right, then we can say scene dot add CW0. Scene dot add this and weights plus equal to CW1, right? So we add the scene, we add this, and we say if weights is smaller or equal to distance threshold, then we call, okay? Then we call graph CW0, right? CW0, and then root scene weights distance threshold city counter, right? So we DFS, but if it's not, then we don't do it, and scene remove CW0 because we have to backtrack weights minus equal to CW1, right? So we blah 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 blah, we do all this. Once we're done, okay, so we need to do int city counter equal to new int n, and we say DFS graph. Actually, we should say for int root equal to 0, root smaller than n, root plus plus. All right, we'll do root new. I guess it's fine. We're just gonna new hash set as a 0 distance threshold city counter. So we do that, right? We do that. Now, some nodes might be visited twice. I realize some might be visited twice because like 2, right? I can visit 2 by going this way or going this way. So maybe the scene should not remove, right? Your weights can remove, but scene shouldn't remove. So the first time you hit, but what if, I think it does require Dijkstra. It does require Dijkstra, right? But, because I need to know the shortest to reach every single node, right? I need to know the shortest to reach every single node. Oh. Madre mia. Do I have to do Dijkstra? Okay, yeah, I do think we have to do Dijkstra in this one. Because I need to know the shortest distance to everyone, so we have to do Dijkstra, and but hold on. I did not use if a node can be reached, right? If a node can be reached, then the counter will just, we'll update the counter. And that node should not be reached again. If a node cannot be reached initially, but it can be reached later, it will still be reached. No, because I still don't think this one requires Dijkstra. That's the thing. I don't think so. I don't think so, but I also don't think I should do this. If I've seen it already, do not do it again, right? Do not do it again. So basically, if it does not contain, I add it to it. We do this. If it's smaller, then we'll DFS. If it's not, then we don't. Basically, we don't go down that path. We try something else, right? And we might as well do the city. I was wondering, where should I do the city counter? Now I do the city counter here, which means the first one coming in, we'll do the city counter. That doesn't feel right, okay? I am going to do the city counter here. Right, I'll count city because this is a legitimate, right? This is a legitimate place to update because the weights, because I'm going to a child, which has not been seen before, and it is within the good distance. So it is something reachable. So I plus, and now we try it. Right? We keep going. Right? We keep going. All right. So based on this, I'll do that. And once I'm done with that, right? Once I'm done with that, what I see is city counter, right? Then what I need to find is return the city with the smallest number of cities that are reachable. So basically we go left to right, we find something that's smaller. If it's something that's smaller equal to, we update. Okay, so int res equal to res equal to city counter 0. Okay, and actually no, this is the min, right? Min is this, int res is equal to 0. Okay, now I say for int I equal to 0. Oh, I see, I can do this in one shot. So min shall equal to, 1000, because it cannot be, right? Int res equal to 0. Doesn't matter actually. So we do this. Right, we do this. And then what I say, I do this and I get it. Alright, I get it. Do I even need a city counter? It'll be easier, right? It'll be easier. Now we just say if city counter root smaller equal to min, right? Min equal to city counter root and res equal to root. Then we'll return root. No, return res here. I am not sure about one thing, because it feels like all I need to return is how many has been, right? How many nodes along the way we have encountered. So every time we encounter, because I am at a current node, right? I'm at a current node, and I want to see right? I want to see if the child, right? I have all these child. How many can be added, right? So from this level, what's the total number? So we just need to add it, right? We just need to add it. So like it's good, we just add it, right? The current one we just add it, and then we'll have DFS, which is, right? So we are adding this. But for each one, I'll DFS that. So from this, how many we can add, which means I think there is a likelihood, not likelihood, a certainty that I don't need this, okay? And all I need is int res equal to 0, right? And each time it's good, we say res plus plus and res plus equal to this, whatever the DFS is giving me, and at the end we will return res. Right? At the end we'll return res, and here I can say int count equal to this. Again, we don't need this. Don't need this, and can say count. All right, and then count. That's int. Okay. Let's see if it works. It works for the first test case. Let's see if it works for the second test case. It does not work for the second test case. That is bonkers. Output should be 0. Shoot. So threshold is 2. Okay, 0 shall have 1. And my output is 1. 1 has 2. Let's see what got wrong here. And I also realized I don't need this root anymore. Yeah, because I don't think that is root even used here. Root is not even used here. So this root can, well, it won't change things. Because I add here, so which means, okay, so we'll need to do something. So set integer scene equals new hash set. Before I get in, scene.add root. Okay, and then scene. And once it's done, scene.clear. Okay, let's try this one. Oopsie doozy. Make some little change. Still not right. And we add root, but that is still not right. How is that possible? Alright, we'll do a little bit investigation, but if we can't figure out, we can do count. So let's say system.out println string.format %d. I need root and count. Alright, 0 is 1 and 1 is 1. 1 is not 1. 2 is 2. 2 is 2. 3 is 2. 4 is 2. 4 shall be 3. There's a lot of issues here. A lot of issues. So 0 is 1, but 1, how come 1 is not? Did I do this wrong? 0, not sure if the graph is right. And then I say for graph, I'll get a default node. We get a node, and we have CW, which has if contains if it does not contain, then we add it. Waits, we'll add it, right? Then we will travel to that. We add the scene. We have the new weights. And we have distance threshold, right? So yeah, if you start from 1, we have 0. You can go to 0. You should be able to go to 4. Alright, you should be able to go to 4. Alright, this seems to be, I think I need IntelliJ. Need debugger for this. Alright, so we have int n is Lord. Distance threshold. Oh, it's not what I want. Okay, then we do this, do this. Oh crap. Yeah, I think there's a better way to do this. Track node is 0. Here go to 1. Uh-huh. 1 and 2. That's good. Scene, add. So scene. Weight is going to be 2. Uh-huh. Now do the next one. Node is 1. Yeah. Node is 1. Yeah. Oh, we first get to 0, right? Node is 1. Huh? Weight is 2. Oh, because it's 0, right? And then CW, we go to 2. Okay. I added. I see. I think I know. So basically, we should not add. Until we get here. There we go. Okay, this one looks more promising. Yeah, we shouldn't add until we decide to add it. That makes sense. Find the number of cities within the distance threshold. Since n is small, we can run DFS with each node as root. Try it. Oh, a wrong answer. Shoot. Twenty. Okay. So from 0, I can reach 1. I reach 2, I reach 3, reach 4, but I cannot reach 5. So 0, I can go to 4, 1, 2, 3, 4, 5. Yeah, well, I reach 5. 2, 1, 2, 3, 4. 3, I can reach 4, right? 1, 2, 3, 4. I can reach 5. I can reach 5. Yeah. 4 can reach 1, 2, 3, 4, 5. Yeah, 4 can reach 5. And 5 can reach 1, 2, 3, 4. 1, 2. I can reach 5 as well. Huh? 20. Then I can go this way. Oh, 5 can reach everything. 0. Oh, 0 can reach 5 as well, I bet. 2. Yeah, can reach 5. Everybody can reach 5. Everybody can reach everybody else. Okay, I can see. I see why. When you reach it, you need to know if you reach it with, if it's reach it with a smaller, then you should still be able to do it. If you reach it with a high, yeah, okay. So it's not seen. Let's call it I don't need to do that. I see. here, so basically we'll say if this 0 is larger than weight So we get a new weight that will reach it, and we say if to reach the distance is so the current weight is smaller, right? Current weight is smaller, then we'll do that. Oh, and then you have to add it again. You might visit it twice. Yeah, you might visit twice. I guess it's fine. I have a new idea. I guess it's fine. And alright, so if the distance, the current distance is larger than the weight, then we will set it to this weight, and then we'll DFS again, right? And once we're done, we'll reset the weight. Of course, we don't need this. This is going to be a void. Okay, so here we have this. And the count, right? C of this count plus equals to D is smaller than 1000. So this is 1, otherwise we do this. And then if count is smaller than n, now we do this. Okay. Oh! Shoot. Oh! Damn. 10 to the 4th. To the 4th. was too slow. Okay, let's try this. Yeah, the weights can be big. Actually, I mean, it's 100, right? It's 100, so 100 times this. Yeah, I think this one should be fine. Let's see. Roll. Test this. Okay, looks all right. Try again. Passes, but very, very slow. Yeah, I do think probably we need Dijkstra this thing. I mean, O squared definitely works, but we probably need a Dijkstra this thing. How would you Dijkstra this thing? I mean, Dijkstra is to find. Yeah, we'll go Dijkstra. And the first node that, I see. The first node that gets the Dijkstra weights beyond the threshold, then we stop. Then however many nodes we have visited so far is the answer. Okay. Okay. Yeah. We can Dijkstra this. But yeah, I don't want to do it today, Dijkstra. I mean, think about it. I haven't written Dijkstra for a very long time. So Dijkstra, basically, you have a root, right? And you need a priority queue. And you put the root in the priority queue. So the root comes out, and you find its children, okay? And you find its children, you have the current weight, right? And then you know the weight that go to each child, and you compare, right? You compare that to an array that stores the weight that they reach each child, you reach each node, and if it's smaller, then you push into the priority queue. If it's bigger, right? If it's smaller, you push into priority queue. We need both. We need the weight, and we need okay. So we do that, and then yeah. Well, I guess we can Dijkstra this. You wanna try? Yeah, I kind of don't want to try it today. All right, what Dijkstra it tomorrow. Okay. What Dijkstra it tomorrow. Now, hopefully tomorrow will be a little bit faster when I do it. Yeah, this is kind of slow because we went through a couple of iterations that didn't work. I mean, this one works, but it's slow. All right, I'll just end it right here. So tomorrow we're gonna try the Dijkstra. I'll see you guys tomorrow. Adios.